In the previous video of the series, we looked into the qubits and some examples of physical systems that can serve as qubits. In today's video, we're going to learn how we can manipulate the state of these systems to perform calculations on a quantum computer. A great way of visualizing the state of a qubit is with the Bloch sphere. This diagram allows us to represent all possible states of a qubit as points on a sphere. For example, an arrow pointing up represents a qubit in the state 0, and an arrow pointing down represents the qubit state 1. Therefore, the probability of a qubit being measured in the state 0 or 1 is given by how close this arrow is pointing in their direction. The main objective of quantum gates is to rotate the arrows of multiple qubits so that we can measure the desired state. For this reason, we have different types of gates that represent different types of rotations. For example, the X gate, which is the quantum version of the classical NOT gate, rotates the arrow along the x-axis by 180 degrees. This gate changes the state of a qubit from 0 to 1 and vice versa. The equivalent Y and Z gates apply the same rotations across their corresponding axes. But what if we would like to do rotations of arbitrary angles? In that case, we would use the Rx, Ry, and Rz gates to rotate along their corresponding axes by the desired angle. In this example, we are consecutively applying rotations of 45 degrees. Another important quantum gate is the HADA gate, as it creates the state of superposition. If we apply this gate to a qubit and measure it on the computational basis 0 and 1, we will get that half of the time we get the state 0 and the other half the state 1. In the Bloch sphere, this state will correspond to an arrow pointing exactly in the middle of the states 0 and 1. It is important to note that there is not an equivalent HADA gate in classical computing, since the state of superposition is a property of quantum systems. The measurement gate allows us to determine the final state of the qubits. Although qubits can be in a superposition of zeros and ones, classically we can only measure one of them, so the measurement gate could be seen as the official translator between the quantum and the classical world. This gate is making the qubit collapse to a specific state, meaning that if we measure the qubit more than one consecutive time, we will always measure the same result. These are all examples of single qubit gates that we can perform on a quantum computer. In our next video of this series, we'll take a look into gates acting on two qubits. Stay tuned for more.